This video lesson is all about what we're going to call the basic exponent rules. And this is going to refer to some operations, namely multiplication and division, that we're going to do with some powers that have the same bases but different exponents, and the ways that we can shortcut some of those operations and combine them more quickly so that we can take long, complicated expressions and eventually simplify them down to smaller, easier to manage ones. And so powers of the same base would be things like 2 to the 4th and 2 to the 6th. So we're going to do a few different things. We're going to try to discover a pattern with the exponents and how they actually interact with each other when we're multiplying powers of the same base. Now, the important thing here is we are not going to evaluate. We're just going to try to combine them. So we're going to use the definition of an exponent. I'm going to ask you to pause the video and tinker around with this for a few minutes and come back when you're ready to see the answer to this one before we move on to the next few, and see what happens when we use the definition of an exponent to take these powers and combine them somehow into a new power. Again, don't evaluate, just use the definition of an exponent and see what you find. So by the definition of an exponent, what we mean is the way that it refers to repeated multiplication. So we have 4 2's here that are multiplied together. We have 6 2's here that are being multiplied together. And of course, these two things are being multiplied together because that's what's happening. So altogether, what we've created is a new longer string of 2's being multiplied together. So 2 to the 4th times 2 to the 6th, in fact, is 2 to the 10th, because we have 4 of these and 6 of these, and together we create 10 total 2's. Let's see if that kind of pattern works with these two exponents here. Again, don't evaluate the ones with the 5's. Just use the definition of an exponent as repeated multiplication to expand and then combine those powers. The same thing where the base is the f. Pause the video and come back when you are ready to see what happens and find a pattern and a rule. So on the left-hand side, 5 to the 2nd is 5 times 5. 5 to the 7th is 1, 2, 3, 4, 5, 6, 7. And altogether, when we make this into one more exponent, one giant exponent, we have 2 5's and 7 5's altogether for a total of 9 5's being multiplied. So 5 to the 2nd times 5 to the 7th is 5 to the 9th. Now f to the 4th is f times f times f times f. F to the 3rd is f times f times f. It's not a great color. I'll have to use a new one here. Altogether, we end up with 4 plus 3, or 7 f's. So that eventual power is f to the 7th. So something you might have noticed during all of these examples is that when we are multiplying two powers with the same base and we are combining them into a single power, what we actually end up doing is just adding the exponents, because the two exponents refer to the number of 2's being multiplied. So when you multiply 4 2's by 6 2's, you end up with 4 plus 6, or 10 2's being multiplied. When you multiply 5 2's plus 7 2's, you end up with 2 5's with 7 5's, you end up with 9 5's being multiplied. When you multiply 4 f's by 3 f's, you have a total of 7 f's all being multiplied. So the basic rule is, if you're multiplying powers with the same base, add their exponents together. And that is your simplified version. So go ahead, pause the video. I'm going to write down, this is called the product of powers property. The name of it, its definition, as well as the numbers and algebra forms of it. We'll talk a little bit about what those mean here in a second, and then we'll move on to what happens when we divide powers of the same base. So it's important, and there's a reason it's underlined in this description, is that the powers have to be of the same base if you're multiplying. Otherwise, you can't take and decompose, if you will, those powers and then combine them back into a single power. The expanded powers have to end up multiplying the same number or variable over and over and over again, so we have to have the same base. With numbers, it's nice and easy to see. F to the 4th times f to the 3rd is actually becoming f to the 4 plus 3, or the 7th. And the algebra over here just says no matter what our exponents are, if they were generic A's and B's. All right, I guess my Florida client is scanning for vulnerabilities there. Good to know. Those A's and B's, then the new exponent is just the sum of A and B. whatever a and b happen to be. Now let's take a look at what happens if we end up dividing those powers instead. Again, use the definition of an exponent, expand it, and see what happens. Don't evaluate, just combine them. Leave it as powers. Try to use what you know about simplifying fractions and expanding exponents to come up with an idea. Come back when you are ready to see what I came up with and what you might have come up with, and then move on to another example here. So in this case, we're dividing. They're on different ends of the fraction bar. So we have 7 2's that are in the numerator. And we have 4 2's that are in the denominator. Now what that means, because we have similar things that are at numerator and denominator, what we can do is cancel one at a time each from the numerator and denominator. These 2 2's will divide out and become 1. These 2 2's will divide out and become 1. These 2 2's will divide out and become 1. These 2 2's will divide out and become 1. And all we're left with is 3 2's in the numerator. So 2 to the 7th over 2 to the 4th is equal to 2 to the 3rd. So you might notice a pattern fairly similar to the one that we saw last time with multiplying, but with a slightly different idea. Let's see if the same thing is true with this example, just with variables. Again, expand those powers using the definition of exponents. Simplify what you can based on what we know about simplifying fractions, and see if you can discover a pattern with variables as well. So in our numerator, we have 9 d's. 1, 2, 3, 4, 5, 6, 7, 8, 9. Important to make sure we have them all. In the denominator, we have 7. So 1, 2, 3, 4, 5, 6, 7. And now we can just pair them off, one in the numerator and one in the denominator, to cancel, because d divided by d is going to be equal to 1. 1, 2, 3, 4, 5, 6, 7 d's that end up canceling. And now we have 2 d's left in the numerator, so d to the 9th over d to the 7th is actually d to the 2nd. So what you might have noticed as a pattern during these things, during these two example problems, is that while when we multiply bases of the same power, we add their exponents together, here we're actually doing the inverse. We subtract their exponent. 7 minus 4 is 3, and that is what turns out to be our exponent in our eventual simplified form. And that's because in the greater exponent, the 2 to the 7th, we can cancel out the number of 2's being multiplied in the smaller exponent, which is 4. So if we start with 7 and we cancel 4 away, what we're left with is 7 minus 4, or 3. Similar thing is true with the d's. If we have 9 d's and we cancel 7 away in the denominator, we are left with 2. So the quotient of powers property that you're going to write down now, the name, the description, as well as the numbers and the algebra, is what is the official property that we're using there. Go ahead, pause the video, write these down, come back when you are ready to talk about it a little bit, and then have a few example problems to do. So it's important to divide 2 powers of the same non-zero base. Remember that 0 can't be our denominator, so the base has to be non-zero in the denominator. We're going to subtract the exponent of the denominator from the exponent in the numerator. So in numbers, x to the 5th over x to the 2nd, 5 minus 2 is 3, so our eventual simplified form is x to the 3rd. In algebra, again, just showing that this works with any number that we could possibly want as our exponents, x to the a over x to the b is just x to the a minus b, numerator minus denominator. So here are 4 problems for you to work on your own. Remember, we can only combine powers with the same base, so use that to try to figure out what to do with multiple bases here. It's not too bad. Just you can do each one at a time and combine their eventual answers. Pause the video, work on those, come back when you are ready to see the answers, as well as move on to one final thought about the product and quotient of powers rules. So in the first problem in the top left, remember that 3 is 3 to the 1st, so the 2 3's can combine to 3 to the 2nd times 3 to the 1st is 3 to the 3rd. 2 plus 1 is 3. And then x's, we have x squared times x cubed, and 2 plus 3 is 5. So make that exponent clear, 3 to the third times x to the fifth, one base at a time, using those same rules that we're familiar with. On the upper right-hand corner, we don't have any a's to change, so the a remains the way it is. But for the b's, now we're dividing, so we're going to cancel 2 b's from the denominator with 2 b's from the numerator and end up with 6 b's remaining. So a to the second times b to the sixth. In the lower left-hand corner, again, combine the different bases and just different steps. 6 3's times, or 3 6's times 2 6's is a total of 5 6's. And then finally, 5 t's times 8 t's is a total of 13 t's, so it's 6 to the fifth times t to the 13th. And then in the lower right-hand corner, we kind of have an option of what to do here. Let's multiply first. That's a total of 8 q's in the numerator, because we're multiplying, so we're adding 3 plus 5 as the exponents, and q to the 8th over q to the 4th, subtract those powers to end up with a q to the 4th left in the numerator. So that's really all there is as far as powers with the same base when we're multiplying and dividing. As a quick review, if you're multiplying powers of the same base, add their exponents. If you're dividing powers of the same base, subtract their exponents.